Hi guys, and welcome to episode 2 of Logical Redstone Reloaded. Last episode, I went over the basics of every redstone component you'll need and how to use fabric mods. Now, as much as I want to start building cool circuits, we have to cover a few more fundamentals first. Specifically, we need to learn about number systems. If I were to describe logical redstone in one word, it would probably be numbers. Numbers make so many things possible, from calculators to game systems to fully fledged CPUs. But how much about numbers do you really need to learn for redstone? I mean, assuming you're above 5 years old, you already know what numbers are and how to use them. Well, as it turns out, the way you learn to think about numbers as a kid is not the only way to do it. It's just the most popular one. At some point, you were probably told that there are 10 digits, 0 through 9. But why are there 10 digits? What if you only had 5 or 7? Would that break things? And if it doesn't break things, how can we exploit it to become better redstoners? To explore these questions, let's go back to school for a second and take a deeper look at how our number system works. Our number system is called base 10, or decimal. It's a positional number system, which means that the value of any digit depends on its position. If a digit is all the way to the right on a number, it's in the ones place. But every place value to the left gets 10 times more valuable. And if you go to the right, even beyond the decimal point, the place values get 10 times less valuable. For example, the number 321 literally represents 3 times 100 plus 2 times 10 plus 1 times 1. But why do we do this? Why do place values have this relationship? Well, I think the easiest way to see why is by counting. Let's say that all you have is the ones place and you want to count up as high as possible. So you start at 0 and start counting up. 1, 2, 3, all the way to 9. And at this point, you've counted up 9 times, you've stayed completely in the ones place, so there's no problem. But if you want to count up one more time, you have an issue. There's no symbol you can put in the ones place to signify a 10. So without making a new symbol, how do you signify that you've counted up 10 times? I mean, you could make another ones place, but then what's going to happen when you get to 30 or 40? That strategy won't scale very well. The genius of our number system is to instead create a new column with more value, the tens place. By doing so, I can package up all the work I did in the ones place into a single digit in the tens place. This 1 is all I need to show that I counted up 10 times. And that's why place values have this relationship. In base 10, every 10 counts of work you do in one place value is equal to 1 count of work in the next place value. Okay, now that we have a good understanding of base 10, let's go back to my earlier question. What if you don't have 10 symbols? Well, let's try it out. Let's say we're using a new number system where there are only 4 symbols, 0, 1, 2, and 3. Just like before, I'll start with a 0 in the ones place and count up. 1, 2, 3. And I ran into a similar problem. There's nothing I can put in the ones place to make a 4. At least, not with these symbols. So, a good solution would be to make a 4's place and put a 1 there. To be super clear, what we're saying here is that the number 1, 0 represents 4 in this new system, because it's 1, 4 and 0, 1s. And that's pretty weird, right? We're so used to seeing 1, 0 and automatically thinking that it means 10. But that's only true in base 10. In this new system that I just created, 1, 0 means 4. And naturally, we'll keep multiplying the place values by 4 as they go to the left. 4's place, 16's place, 64's place, etc. As you might have guessed already, this number system is called base 4. And the amazing thing is, nothing broke. There's nothing wrong with expressing numbers in base 4 instead of base 10. In fact, every number in base 10 has a base 4 equivalent. For example, 32 in base 10, or 32, is 200 in base 4. 3 10s and 2 1s is equivalent to 2 16s. And speaking even more generally, you can express numbers in whatever base you want. Let's say I wanted to express 123 in base 7. The base 7 place values are going to multiply by 7, so 1, 7, 49, etc. And I can only use 7 symbols, 0 through 6. As it turns out, 123 is made up of 2 49s, 3 7s, and 4 1s. So 2, 3, 4 is 123 in base 7. Okay, now we know how bases work, and it's clear that every base is an equally valid number system. So if our goal is to express numbers with redstone, which base should we use? Well, if we pick a base that naturally resembles the state of redstone, it'll probably make things a lot easier. There are 2 common ways to view the state of redstone. You can view it as just on or off, giving you 2 different states, Or you can view it in terms of its signal strength, which gives you 16 different states, 0 all the way to 15. As a result, the most common bases to use with redstone numbers are base 2 and base 16. Let's talk about base 2 first. Base 2 is also called binary. It uses two symbols, 0 and 1. Typically, redstone that's off is used to represent 0 and on represents 1. Just like every other base, we start with the ones place, and then the place values scale by the base. In this case, they go 1, 2, 4, 8, 16, etc. As a quick example, let's convert 25 into binary. I can make 25 with 116, 18, and 11. I don't need anything else, so let's fill these in with zeros. And there we go. 25 in binary is 11001. If you're brand new to binary and want some more practice, try these conversions out. Getting comfortable with binary is really important for logical redstone, so I highly recommend it. For some terminology, a single 0 or 1 can also be referred to as a bit. Therefore, 25 in binary is 5 bits long. Just be a little careful with that though, because, for example, 25 can also be an 8-bit number. All you have to do is add 3 more zeros to the left, and now you have an 8-bit representation for the number 25. And by the way, 8 bits is so commonly used in computer science that it actually has a special name. It's called a byte. With that being said, let me ask you a question. How many different numbers can you represent with 1 byte of information? Pause the video now if you'd like to try to find the answer. Alright, welcome back. The correct answer is 256. There's a few different ways you could have gotten that answer. You could have looked at it as a combinatorics problem. I have 2 choices for each bit, and so 2 times 2 times 2 8 times, or 2 to the power of 8, is 256. You could have also noticed that the smallest number we can represent with 8 bits is 0, while the biggest number is 255, and the range from 0 to 255 has 256 values. Either way is equally valid. The point is, in general, n bits of binary can represent 2 to the n unique values. Now let's talk about hexadecimal. Hexadecimal has 16 symbols because it's base 16, 0 through 9, and then A, B, C, D, E, F. You don't usually see letters in numbers, so this can be kind of weird to get used to. But the most natural way to view it is that A means 10, B means 11, all the way to F means 15. And as expected, our place values go 1, 16, 256, etc. So, as an example, let's figure out what the hexadecimal value 9BF is in decimal. We have 9 times 256 plus 11 times 16, because B is 11, plus 15 times 1, because F is 15. After doing the math, we can see that 9BF in hexadecimal is equal to 2,495. And yeah, there's not a ton I can say about hexadecimal other than saying it's really useful to know. In my experience, I don't use hex as often as binary, but considering that signal strength values are literally made to be hex digits, it can be a really useful tool. The last thing I want to show you in this video has to do with the relationship between binary and hex, because it's really cool. You see, since 16 is a power of 2, converting from binary to hex or from hex to binary is really easy. So easy that you don't even need a calculator. Let's say I have this long binary number. I don't even know what the number is, but to convert it to hex, I don't have to. All I have to do is split it into groups of 4 bits starting from the right, like this. Each group of 4 bits is exactly representative of 1 hex digit. If you look at this first group, we have 0110, which is binary for 6. The middle group, 1111, is 15, or F, and the last group is 4. Therefore, this binary number in hexadecimal is 6F4. And that's it from me about number systems. Like I said, binary and hex are super important for logical redstone. I highly recommend getting comfortable with them. Next episode, we'll start talking about logic and build our first redstone circuits. I'll see you there. I hope you learned something. I hope you enjoyed. Peace out, guys.